What if I told you that the monster storms on Jupiter and a summer thunderstorm on Earth are built from the exact same instruction manual?
I know, it sounds crazy, right? One's a gas giant where storms are bigger than our entire world, and the other is, well, home. But what if the same basic physics, the same rules, are shaping the weather on both? It's one of the biggest questions in planetary science.
And it turns out the answer is a huge yes. Beneath all the chaos, the weather on literally any planet seems to boil down to just a handful of surprisingly simple rules.
To crack this code, scientists back in 1988 did something that still sounds like science fiction. They built an entire planet inside a computer. They created this digital world where they could be the gods of climate, tweaking the master controls to see what would happen.
And what they found was incredible. It turns out all the wild, complex weather systems we see out there are all just made from a few basic patterns. Seriously, think of them like Lego bricks. You only need a few different shapes to build an entire city, right? It's the same idea for atmospheres.
The scientists found 4 of these building blocks. They're basically just huge planet-sized conveyor belts of air, each moving in a specific way. The mind-blowing part is that the weather on any planet is just a different combination, a different recipe of these same 4 basic ingredients.
So that leads to the ultimate question, doesn't it? If it's all just a recipe, what are the master dials? What do you turn up or down to change a planet's entire climate? Well, they found 2 main ones, and the first one is all about speed.
So let's talk about rule number 1, the speed dial.
It's honestly that simple. One of the biggest things that determines what a planet's weather looks like is just how fast it's spinning on its axis. That one number dictates the entire structure of its atmosphere.
And the difference is, well, it's night and day. If a planet spins slowly, its weather is super simple. You basically get one giant, stable weather system in the northern hemisphere and one in the southern. But if you crank up that rotation speed, the whole system shatters into dozens of smaller, chaotic jet streams, creating a mess of local storms.
So the takeaway is this. Slow spin, simple weather. Fast spin, you get stripes. Lots and lots of stripes. This is exactly why Jupiter, which spins incredibly fast, is covered in those famous bands. They're a direct result of this first universal rule. But that's only half the story.
That brings us to the second master control, the other big knob you can turn. And this one is what I like to call the moisture engine.
We're talking about the secret power of water. See, when water vapor turns back into a liquid, like when a cloud forms, it releases a huge burst of energy into the atmosphere. This is called latent heat, and it's like a hidden power source, a secret engine that can supercharge a planet's weather.
The computer simulation showed this perfectly. On a dry planet, the tropics are kind of boring. The energy is spread out. But the moment you add moisture, bam! The tropics just ignite. That latent heat creates super-focused storms and a really powerful jet stream. In fact, one of those 4 Lego bricks of weather, the one scientists call the quasi-Hadley element, it only shows up in a moist atmosphere. It's literally powered by water.
So you can think of moisture as a turbocharger for a planet's weather, especially in the tropics. It doesn't just make things wet, it concentrates energy and creates the powerful weather systems we know so well here on Earth.
Which, of course, leads to a completely mind-bending question. If moisture is the key ingredient for intense, tropical weather, could a bone-dry desert world ever have the same kind of climate as a wet, tropical world like ours? The answer seems like an obvious no, right? But the simulation found a secret back door.
And this is where it gets really good. This is the climax of the whole experiment, the ultimate climate hack.
The answer from the simulation was a shocking yes. A dry desert world absolutely can have the same climate as a wet tropical one. It seems impossible, but there's a catch.
You just have to find a different way to get that energy into the system. You don't actually need the water, you just need intense, concentrated heat coming from the ground. So here's the genius thing they did. They took their dry planet model, the one with the boring, weak weather, and then they just blasted the equator with a ton of extra heat from the surface, perfectly copying the energy that moisture would normally release. And guess what happened? The dry planet, it spontaneously created a powerful tropical jet stream, the exact same one that was supposed to only exist on the moist planet. I mean, listen to what the original paper says. Enhanced surface heating in a dry model imitates latent heating and produces a tropical circulation resembling that of the moist element. They basically tricked the dry planet's atmosphere into behaving as if it were wet.
Let that sink in for a second. The real secret ingredient for wild, dynamic, Earth-like tropical weather isn't actually the water. It's the concentrated energy. Water is just how Earth does it. This means a totally dry planet, one with maybe a belt of super hot volcanoes around its equator, could have weather just as intense as our own rainforests.
And that leaves us with a huge final thought. For decades, our search for life on other planets has been guided by one mantra: follow the water. But if concentrated heat, not water, is the true engine of dynamic climates, what does that mean for our search? Have we been looking for the right thing all along? Could there be dry, seemingly barren worlds out there with atmospheres just as complex and active as our own?